We've got our warm-up problem because last time we talked about vectors, so we should do something with vectors. And if you look at the back of the sheet in our packet, you might notice that vectors didn't seem to have a lot of problems about them, but that's because it's a very fundamental idea underlying things. So you definitely need to make sure you understand vectors. And you can work in different dimensions. We'll focus mainly on 3 dimensions, but this is a problem involving 2 dimensions. You can see because there's 2 slots. So it says, suppose you have 2 vectors in dimension 2. One of them looks like 4, 1. The other one looks like 3, -1. And now the question is, if I take 2 times the first vector minus 3 times the second vector, what do we have? Is there an answer? Does someone work it out?
D.
D? Okay, I'll believe you. I can't remember. Let's figure it out, right? But that sounds pretty good. That sounds pretty good. Now, what's going on? Well, there's 2 ideas here. Scaling and adding. Those are 2 fundamental things we can do with vectors. So we say, all right, so we have 2, and now we'll just replace the vector u by 4, 1, minus 3, and we'll replace the vector v here, 3, -1. And, well, I like to do the scaling factor first. So we'll put those in. So the 2 will go in. That'll give us the vector 8, 2. The 3 we can go in, minus the vector 9, -3. So that's the scaling. Adding, subtracting. What do? Well, you do what you think should be the obvious thing, which is just work entry by entry. So 8 minus 9, and 2 subtract -3, giving us -1, 5. Yes, D. Good. Whew. The right answer was there. Now, what's the punchline? Well, one thing, it's not too bad. Working with vectors can be pretty pleasant. Now, the other thing you should get from this is like, term by term. That seems to be the motto. Yeah, that's true in a lot of things, especially as we start getting into calculus involving vectors, which is where we're heading. And it turns out to do calculus, you only need to have a couple of things. One is you need to be able to add. 2, you need to be able to scale. And 3, you have to have a notion of limit. And the good thing is we can do all 3 of those, and we do them term by term. And we'll get more into that later on. All right, well, where are we going? Our thought for the day, little by little, a little becomes a lot. A proverb from Tanzania. Well, of course, this same idea shows up in a lot of cultures, a lot of places. And that is, most progress is incremental. But as long as you keep making progress, as you keep moving forward, it grows. Don't be frustrated that things are not changing rapidly. Life is not like the movies. There's not going to be a big aha moment. You just keep at it. And as you keep at it, you'll be able to achieve great results. So, all right, now, what's our goal for today? We're staying with vectors, and indeed, we're going to stay with vectors this whole week. We're going to introduce something called the dot product and explain what that is, and allows us to do a couple things. We'll talk about the angle between vectors. That turns out to be related to the dot product. And by the way, you might notice that there's this notation here, the dot. So you know there's a dot product involved if you see a dot. All right, so there's angle between vectors, and it involves the cosine. So the dot product is somehow attached to cosine. It allows us to test for perpendicular. We like perpendicular. Perpendicular has lots of nice things going for it. And, well, perpendicular means a right angle. Cosine of a right angle is 0. So it really just says check the dot product. Dot product equals 0, life is good. The other thing we'll talk about is projection. which is to say we have two vectors. How much of the first vector points in the direction of the second vector? There's a formula for that. And I should note that these formulas here are indeed on the formula sheet. So make sure you know how to use these formulas and how to find what you need. So this is today. We're talking about these two entries on our formula sheet. All right, that's where we're going. Okay. Well, where to begin? Well, we did an example where we talked about working with vectors at the very beginning. We said, well, you can add. And when you add vectors, you do it in the logical way, entry by entry. So you add the first entries up, you add the second entries, you add the third entries. You can scale. And when you scale a vector, you do it in, well, hopefully the obvious way. You scale each entry. You say, well, okay, add, scale. What about multiply? Now, the first thought that people have is to say, well, I like this entry by entry idea. Let's try it out. Take two vectors, multiply the first entries, multiply the second entries, multiply the third entries. There's a new vector, right? And, well, good news is, hey, it's easy to do. Bad news is, it's useless. Now, that's a bold claim to say something is useless. I want to explain what I mean by that. What I mean is that it doesn't have a good geometrical meaning. In other words, if you change your coordinate system, you change fundamentally the answer. So it's somehow dependent not on space, which is what we mean by when we say geometry. It's dependent upon how you're describing the space, which is not what we want. So that's why we say it's not good for us. So the obvious thing is not what we're going to do. So what can we do? Well, turns out there are still useful ways to multiply vectors. And we're going to talk about the dot product. And make a side note here. This works in any dimension. Now, it starts off in a similar way. When we talk about the dot product of two vectors, we still multiply the first entries together, and we still multiply the second entries, and we still multiply the third entries, however many entries we have. But now, instead of forming a new vector, we get a number. So the dot product says a vector dot a vector, and make sure you mark the notation. Spoiler alert, if we're emphasizing notation, it probably means there's a second way to do things. That's next time. So vector dot vector, out comes a number. I haven't justified that this has good geometric meaning. We'll get there. We'll build up to that. But all right, at the very least, it's not so hard. It's a quick computation. Multiply corresponding entries and add them up. Now from this you can get a couple of properties pretty quickly. One thing is it doesn't matter the order that you take the dot product in. U dot V is V dot U, because the same resulting sum of terms is the same. Anything dot the zero vector is zero. Hard to recover when you multiply all the terms by zero. Let's see, what else do we have? This is a good one. U dot V plus W is U dot V plus U dot W. In other words, distribution works. And this is nice, because if we can distribute, we can FOIL. Which means if we have like a something dot something, we can do our first, outer, inner, last type idea. And one more thing I'll add in, which might be useful for one of the quiz questions for next week, is if you scale, so here I have two scaling factors, K and L, I can pull the scaling factors out in front. Again, all these properties follow just using the definition. No big surprises. All right. Well, where are we going? We want to get a good geometrical meaning for this. That's our goal. So, we can start by just saying, well, what happens if I take the dot product of a vector which is self? So I have a vector ABC, and I take u dot u. Well, what comes out? You multiply the first entries together, a squared. Second entries, b squared. Third entries, c squared. A squared plus b squared plus c squared. That's not so bad. We've seen that before. It looks a lot like magnitude. Only thing missing is there's no square root. So we say, okay, well that means it's the magnitude squared. All right, so that's something. Not yet enough, but something. All right, so we have a toehold. All right, now, we're going to do a quick flashback to trigonometry. Ah, the good old days. The law of cosines. So don't worry, you don't have to know this. You can look it up. But law of cosines, you can think of it like, what's the Pythagorean theorem when there's not a right triangle? Now, if you have a right triangle, you get the c squared equals a squared plus b squared. It turns out, the law of cosines says, hey, if you put any angle here, not just a right angle, then you can relate the lengths by c squared is a squared plus b squared, but then there's this extra minus 2ab cosine theta. So if theta happens to be a right angle, cosine theta is 0. And you get Pythagorean theorem. All right, so here we go. I have two vectors, u and v, and I put their tails together. And remember, we're allowed to do that because we can always move vectors into a convenient location. So for us, the convenient location is to have them with their tails together. And once I do that, there's an angle between the two vectors, and I'm going to call that angle theta. So I have a vector u, I have a vector v, I have an angle theta. Well, I claim that this third side of this triangle is the vector u minus v. Now that might not be so clear, but let's think about it. If I added v plus this vector, what's the equivalent vector? V plus this is the same as doing what? It's the same as doing u. Because if you think about net change, right? Vector's about change. So I change again. My net change is going from the initial start to the final end. So v plus this unknown vector is u. So this must be u minus v. Now, a question. What's the magnitude of this vector squared? Well, okay. Do we have ways to compute the square of the magnitude of a vector? Dot product. Okay, so let's do that. So, if you do that, method 1, the dot product. So you take u minus v dot u minus v. All right. Now we say, we mentioned, since we can distribute, we can FOIL. And we start thinking about, well, what does that mean? Well, we take the first and the last, the first, that's u dot u. The outer is a u dot v. The inner, well, that's v dot u, but that's the same as u dot v. So there's really minus 2 of those. And then the last will be a v dot v. So we get the magnitude of u squared, the magnitude of v squared, and then this extra term, minus 2 times the dot product. All right, so good news. We know how to compute the magnitude of that vector. Is there another way we could compute the magnitude of u minus v? Law of cosines. This is a triangle. And I can say, well, let me not worry about it having vectors involved. I just say each side has a length and there's an angle. So we can call this our A, we can call this our B, and this we can call C. So we say, great, law of cosines. So we're going to get A squared plus B squared minus 2AB, so there's AB cosine theta. And here's the great, ooh, we did this in two different ways. But we can't have two different values. Everything has to match. So the great aha is that these two terms, which is how they differ, must match. So we come to the conclusion that u dot v is the magnitude of u, magnitude of v, cosine theta. Or put another way, cosine theta is the dot product of u and v divided by the magnitude of u, magnitude of v. All right. So what's the moral here? Dot product gives us some information. It relates to how the vectors are connected in some ways, the angle between the vectors. That's the geometrical meaning. Any questions? The good news is you don't have to know the justification. It's good enough to know there is justification. It's not magic, but there's this nice relationship. All right. So, to emphasize that we have geometry, this first example. Given vectors u and v, the magnitude of u is the square root of 8. The magnitude of v is 3. And the angle between the vectors. And so, again, to emphasize, when we talk about angle between the vectors, you put the tails together. That angle is 135 degrees. Find u and v. Now, all the information given here is geometry. We're talking magnitudes and angles. So if we can find the dot product, that means we have a geometrical type thing. It's a very useful tool. So what do? Well, we want u dot v. What do we know about u dot v? That we may have learned about in the last couple minutes. Do we have a formula for it? Do we possibly have a formula for u and v? We're dotted together. Yes, yes. Aha! So what can we say about u dot v? Magnitude of u, magnitude of v, cosine theta. All right. Do we know the magnitude of u? Square root of 8. How do we know it's square root of 8? Yeah, they told it to us. Oh my gosh, it's like they want us to do stuff. Do we know the magnitude of v? It's 3. Again, they told us that. And now, do we know what theta is? 135. I know you're thinking degrees. Ugh. I thought we wanted radians. We sometimes do either one. All right, now, does anybody remember the cosine of 135? If it helps, it's a lot like cosine of 45, but it's negative. Ah, I'm impressed. You know your You're cosine 45. So it's the negative of cosine 45. All right, well, I have a square root of 8 times the square root of 2. If I put those together, what does that give? Square root of 16. We'll simplify that in a second. Then we have a 3. Don't forget there's a negative 1, and we have a 2. And people said, square root of 16 is 4. 2 can go into 4. So altogether we get negative 6. So this is an example of how we're using geometrical information to find the dot product. All right. Next question. Find cosine theta. And by the way, if you see a problem that says cosine theta, you should think, this is a dot product question. That should be your train of thought. Find cosine theta, where theta is the angle between the vectors, 1, 3, negative 2, and 2, negative 4, negative 6. Do we have any answers? Cosine theta equals 1 over 14? Okay. I don't know. I haven't done it yet. Could be. But there's an answer. Okay. Anybody else get 1 over 14? Oh, a lot of people got 1 over 14. All right, good. So let's see how we got it. So what do we need? Well, if we want to find cosine theta, it's a dot product, u dot v, over a magnitude. Magnitude of u, magnitude of v. So we do the dot product. Multiply entries. 1 times 2, 2. 3 times negative 4, negative 12. Negative 2 times negative 6, positive 12. All right, now that's the upstairs. Downstairs we have a magnitude. All right, so we're going to take a square root, and we square each entry. So 1 squared is 1, 3 squared is 9, negative 2 squared is positive 4. When you square a negative, you get a positive. And then the other term, square root of 2 squared is 4, negative 4 squared is 16, and negative 6 squared is 36. All right. Now we say, well, simplify. The 12s cancel. That's a good sign. 1 plus 9 plus 4, also known as 14. Now, 4 plus 6 plus 36. Well, 4 plus 16 is 20. Add 36, that's 56. Also known as 4 times 14. So what do we have? We have 2 upstairs. The square root of 14 is the first term. If I take the square root of 56, I can take the square root of 4 and the square root of 14. Square root of 4, that gives me hope. Square root of 4, also known as 2. So we get cancellation. Square root of 14 times square root of 14 is 14. All right, good. Now, there is one quick check. This isn't a perfect check, but you can catch at least an error. If you're asked to find cosine of an angle, and your answer were, let's say, 5/4, did you get the right answer? Why not? I hear no's. Why not? It's bigger than 1, right? Anytime you find a cosine, it can't be bigger than 1, and it can't be smaller than negative 1. So it was a good thing that it was between 1 and negative 1. I did forget to mention one other thing. I do want to talk about, people asked, how do we think about what this is telling us? This dot product thing. I like to say it's giving you information about how closely the vectors are pointing in the same direction, or maybe they're pointing in opposite direction. There's a fun application of the dot product, which is dating websites. What you'll often do is you'll fill out surveys. And then they'll say, well, based on your survey responses, here are some matches. Well, what are they doing? Well, what they're doing is they're turning your survey responses into a vector. And then they say, okay, let's take the dot product of you with other people. The closer you get to a large positive number, that means you're more closely aligned. A large negative number means you're opposites. And so they say, okay, let's find you matches where your dot product is a large value. So yes, math does get involved in interesting things. All right. So, as we mentioned here, this is sort of just a way to say this. Cosine should be between -1 and 1. If you find out that you get cosine of theta equals 1, that says you something about the vectors are pointing in the same direction, exact same direction. If you get a positive value for cosine, it says the angle between the vectors is acute. So as long as u dot v is positive, either they're pointing the exact same way or at least it's an acute angle. On the other hand, if cosine turns out to be negative, you're pointing the exact opposite way. Or if you're between 0 and -1, you're at an obtuse angle. But there's the sweet spot. If you have cosine theta equals 0, that means the dot product is 0. When that happens, when the dot product is 0, we say it's orthogonal. And we oftentimes use the word perpendicular. They're almost the same thing. There's a slight technicality, but we'll use them interchangeably. But we say, okay, that's our sweet spot. Now you might say, why do we like that? Well, you'll discover that we love perpendicular. So for instance, when we get to thinking about things geometrically, we say, I want to find the shortest distance between things. Oftentimes, that means there's a right angle involved. So we like right angles. It shows up geometrically. So this is the sweet spot. Put a little bit of this is what we love. All right, let's see. Do we have enough time to finish this problem? We do? Oh, okay. All right. Apparently we do. There's another topic, but all right. We'll do this one quickly. Find all values t so that we have two vectors which are expressed in terms of t. And that's perfectly fine. It just means as you pick a value for t, you get a slightly different set of vectors. We're going to move into this setting in the next few weeks. We want to make sure they're orthogonal. So when you hear the word orthogonal, what should you think? What's your go-to?
Right angle.
Right angle. Orthogonal says, hey, we really want their dot products to be 0. So if you hear orthogonal, a little light in the back of your head should turn on and should be dot product is 0, dot product is 0, dot product is 0. That's how we're going to do our orthogonality. So you say, great. Now we have a plan. 0 is equal to this dot product of these two vectors. And we say, all right, well, we know how to take dot products of vectors, so let's do that. So it would be t squared minus t minus 1 times 2t, that's the product of the first two entries, plus t squared times 3 minus 2t, product of the next two entries, and then 2 minus t, add 2 minus t times minus 1, product of the last entries. Say, all right, well, now we have here, it's a polynomial. So we say, oh, this really just is about polynomial equals 0, solve for the roots. Well, we can distribute. We'll go ahead and do some things here. We'll take the 2t through. So that becomes 2t cubed minus 2t squared minus 2t. Here we'll take the t squared through plus 3t squared minus 2t cubed. Here we'll put the minus 1 through minus 2 plus t. And fingers crossed, good things will happen to us. If we've lived a good, clean algebra life, good things will happen to us. Well, okay, anything good happening to us? The 2t cubes cancel. Nice! How about the t squareds? What are we up to? There's just 3t squared and minus 2t squared leaves us with a single t squared. How about the t's? Yeah, we're left with a single minus t, and then finally we have the constant. So we say, this reduces to solving 0 equals t squared minus t minus 2. That feels like something we can do. It almost feels like it should factor, because our teachers love to give us things that factor. I claim it does. T minus 2 times t plus 1, check it out. T squared, good. T minus 2t, minus t, and minus 2. So, what does that tell us about t? 2 or minus 1. And there you go. Nice. Nice. All right. Now, one last idea for today. And to motivate it, imagine, if you will, that you have a car. So I will draw this. This is a car. You can tell it's a car from this picture because it says car. And you might imagine that the car is having difficulty. Maybe it's an older car, maybe it's winter, who knows, but for whatever reason, it's stuck and it can't move itself. So you get some people, because this is Iowa. I saw on social media, everybody's so nice here. I like to say that's true. So you get some friendly people and they start pushing the car. And you have some people push from the back. Then some other people are like, I want to join in on the fun. And they push from the side. And the goal is they're trying to move the car in this direction. Now a question. Are the people pushing from the side as effective as the people pushing from the back? Why not? Everybody was like, no. Not parallel to the direction, yeah?
If you break up like the coordinates of their x and y after the force is coming, the left and right now.
Yeah, like some of the force is pushing into the car, not nice to the car, and some of it's pushing in that direction. Now, by the way, force has two components. A size of the force, or if you like, the amount of force, and the direction it's being applied. So it's a vector type thing. So it raises the question, if I want to understand how effective the people are on the side, I want to understand how much of their force is in the direction of movement. So there's a question, how much of one vector is in the direction of another vector? So that leads us to the notion of projection. Okay, so here's the idea. We're going to denote this projection, P-R-O-J for projection. We're going to project the vector u onto v. How much of u is in the direction of v? That's our goal. Now, I like to think of the word projection almost like a shadow. So imagine that you have these two vectors. I have v, and I have u. And there's this light source from on high. And it's casting a shadow. And what you see is there's this sort of thing falling down, forming a nice right angle. And this part of u, that's the projection of u onto v. So this is how much of u is pointing in the same direction as v. Now that's the picture. How do we actually find it? Well, if I'm trying to find a vector, there's two things I have to figure out. What's the direction of the vector? How long is the vector, the magnitude? If I can answer those two questions, I win. I have the vector I'm after. So, that's what we're going to do. We're going to find our vector in this way. You say, okay, I know the direction because I want it to be in the direction of v. So I go to v and I say, okay, v, give me your direction. Well, how do I find direction of a vector? We look at the unit vector. The unit vector gives us direction. So our desired direction, 1 over magnitude of v times v. That's the unit vector pointing in the direction of v. Now for magnitude. And you might notice I put it in quotes. The reason I put magnitude in quotes is I do recognize cosine theta can be negative. I'm not going to go through, but it does what it needs to do. I'll say that. So how do I find that? Well, I come here and I say, I have this lovely picture. And I can think about it as there's a right triangle. The hypotenuse, that comes from u. So that's length of the hypotenuse is the magnitude of u. And I have this angle theta. And I say, well, I want to know this length right here. So what relates the hypotenuse and the adjacent? Cosine. Cosine theta is the adjacent divided by the hypotenuse. So the length of this side is cosine theta times the hypotenuse. So that's the magnitude. Now we have direction and magnitude. So we multiply. Scale the direction by the magnitude, and we win. So the projection, u onto v, magnitude of u cosine theta, times 1 over magnitude of v times v. Like, okay, great. Well, that's not easy to remember. Then we say, well, okay, there's a cosine theta. And cosine theta looks a lot like a dot product. And as we look at it, it says, well, I already have a magnitude of u and a cosine theta. I'm really close to a dot product. What would I need to get a dot product? What's missing? Magnitude of v. So if it's missing, we put it in. How do we put it in? We multiply both top and bottom by magnitude of v. So that's where this magnitude of v comes from. There was already a magnitude of v downstairs, so that's magnitude of v squared. So now the upstairs is a dot product, u dot v. The downstairs is also a dot product, v dot v. So u dot v over v dot v, all that times the vector v. Now you might say, oh, it kind of makes sense, right? Because what do you want to do? You want to say, oh, I know, if I just cancel off the v's, the only thing left is u, and that seems right. That doesn't work that way. That's okay. But that's the formula. Now, that's how much of u points in the direction of v. What if I didn't want that question? What if I wanted to ask a different question? How much of u points perpendicular to v? Can we figure that out? Aha, someone looked ahead. Yes. Yeah. We can do sine, and sine is coming. Don't worry. Sine is definitely coming. But it's like, look, if you already know 2 out of 3 sides of your triangle in terms of the vector, you can get the missing side in terms of the vector. You say, well, okay, this part plus this part has to make up u. So if I take u, subtract the projection of u onto v, that's the part that's perpendicular to v. So you can answer questions, how much is parallel, how much is perpendicular. Any questions about the theory? Yes?
When you do like the dot products divided by each other,
Right.
like if you're multiplying, wouldn't they end up being the same thing?
Well, I mean, notice that we have different vectors, right? U and v, and here is v and v. So there's not like cancellation. And yeah, you have to be careful. And you're just like, oh, my algebra teacher was big on cancellation. But no, don't be creative. Math is if there's a whole different college for people who want to be creative. This is not that college, right? Engineers, don't be creative. Follow the rules. Follow the rules.
Do we have to write it as v dot v and just keep it as
You don't have to memorize it in this format, but this is the format that's given on the formula sheet. So, all right, we have a couple of minutes. Should we do one quick problem?
yes.
All right. It's a quick one. Find the projection of u onto v. And we say, hey, pull out the formula sheet. I'm not going to reinvent the wheel. I'm just going to look up the formula. And that's u dot v over v dot v times v. So what do? Well, we say, let's take u dot v. Now, notice this is slightly different notation. This is your ijk notation, not component. You can work in either one, but if you like component, what's another way to write minus I plus 5j plus 2k? Minus 1, 5, 2. This one, 2i minus j plus 4k, 2 minus 1, 4. That's minus 1. All right, so u dot v. Minus 1 times 2, minus 2. 5 times minus 1, minus 5. 2 times 4, 8. Downstairs. Now this is when you have to pay attention. Which one is the right one? Well, it's the one you're projecting onto. That's where you take the dot product with itself. So this is what we're projecting onto. So v dot v. 2 times 2, 4. Negative 1 times negative 1, 1. 4 times 4, 16. Okay. Times v. 2 minus 1, 4. Minus 2 minus 5 plus 8 becomes 1. 4 plus 1 plus 16 becomes 21. 2 minus 1, 4. What's the next thing for us to do? Put it in a box, because this is the projection. Now, depending on the problem, they might ask us to write in a very specific form, but that's the projection. That's how quickly it can go. Once you have the tools, life is good. All right, we'll continue next time. Have a good day.